Welcome back to the class of chemistry. My name is Gurinder Pal Singh. Hope you all are fit and fine. My motive for this video is to make you understand the methods of preparation of ethers, physical and chemical properties of ethers, and some important conversions. This lecture is going to be super excited for you, so let's start. Before starting, I'll recall the structure of ethers. Well, my dear students, ethers have structures similar to that of water. In this case, oxygen undergoes sp3 hybridization, forming 4 sp3 hybrid orbitals. Students, 2 of the 4 sp3 hybrid orbitals of oxygen atom overlap with sp3 hybrid orbitals of 2 alkyl groups, forming sigma bonds. Now students, what is sigma bond? This is the concept of class 11. Let me recall you. Students, a sigma bond is a type of chemical bond. It is the strongest one of the covalent type. In sigma bond, the atomic orbitals from two atoms which are nearby go one on top of each other. This is different from a pi bond where they touch sideways. In simple terms, single bonds are sigma bonds and pi bonds are double or triple bonds. In the first structure, there is a single bond, that is sigma bond. In the second structure, first bond is sigma bond and second is pi bond. And in third structure, there is triple bond. It means first bond is sigma and rest of two are pi bonds. So let's continue with the structure of ether. I was saying that 2 of the 4 sp3 hybrid orbitals of the oxygen atom overlap with sp3 hybrid orbitals of 2 alkyl groups, forming sigma bonds. And the remaining sp3 hybrid orbitals of oxygen contain a lone pair of electrons as shown in this diagram. Students, the larger bond angle in ethers may be because of the greater repulsive interactions between bulkier alkyl groups as compared to the smaller hydrogen atoms in water. Thus, ethers have bent or angular structure. Now we will study the methods of preparation of ethers. So my dear students, first method of preparing ethers is dehydration of alcohols. Well students, simple or symmetrical ethers can be prepared by the dehydration of alcohols with concentrated sulfuric acid at 413 Kelvin. But if temperature will be 443 Kelvin, then ethene will be produced. So students, the formation of product alkene or ether depend upon the reaction conditions. Now we will do the mechanism of formation of diethyl ether from ethanol. Students, in chemistry, a reaction mechanism is a step-by-step sequence of elementary reactions by which overall chemical change occurs. So let's start the mechanism for the formation of diethyl ether from ethanol at 413 Kelvin. Well, in the first step, ethyl alcohol gets protonated in the presence of H positive ion. Actually students, alcohol initially gets protonated in the presence of acid. And here we are using sulfuric acid, that is H2SO4. The acid dissociates and hydrogen ion protonates the oxygen atom of ethanol, giving the ethanol molecule a positive charge. That's why it is called protonated alcohol or ethyl oxonium ion. Students, in the second step, the carbocation formed by the ethanol in the presence of acid is open to attack by nucleophile. And very interesting thing here is that ethanol with lone pairs on oxygen atom is itself a nucleophile. So it attacks on the carbocation. So the nucleophilic oxygen atom of unprotonated ethanol then displaces a water molecule from protonated ethanol molecule, producing water and oxonium ion. Or we can say that there is nucleophilic attack of unprotonated alcohol on the protonated alcohol molecule, and the reaction follows bimolecular nucleophilic substitution mechanism, that is SN2 mechanism. In the second step, we will get protonated ethoxyethane, that is oxonium ion, and water is also eliminated. This step is slowest step, and one very important thing that I would want to tell you, slowest step is a rate determining step. Means if step is slow, it will affect the rate of reaction. And now finally in the third step, oxonium ion loses a proton to form an ether. So students, this is how we get the diethyl ether from ethanol step by step. This step is fast and does not affect the rate of reaction. Limitation of this reaction is that this method is suitable for the preparation of ethers provided the alcohol is of primary nature and temperature is low, that is 413 Kelvin. At a temperature of 443 Kelvin, dehydration of primary alcohol results in alkenes as the elimination product. The reaction, however, follows SN1 mechanism. Secondary and tertiary alcohols give alkenes as major products under the reaction conditions. Like in isopropyl alcohol, major product is propylene and minor product is diisopropyl ether. Similarly, in tertiary alcohols, the major product is 2-methylpropene. So students, the order of dehydration of alcohols to form ethers is primary is greater than secondary is greater than tertiary. Students, if I'll talk about another limitation, so this method is generally not used for the preparation of unsymmetrical ethers also, because mixtures may be obtained. For example, in this reaction unsymmetrical ethers are obtained, but there is a mixture of these ethers. So students, these are the limitations of obtaining ethers from alcohol. Next, we will obtain ethers from alkyl halides by Williamson synthesis. My dear students, this is one of the best method of preparing symmetrical and unsymmetrical ethers in laboratory. In this method, an alkyl halide is treated with a suitable sodium alkoxide prepared by the action of sodium on suitable alcohol. The reaction involves nucleophilic substitution SN2 attack of an alkoxide ion on primary alkyl halide. Similarly, alkyl aryl ethers, that is phenolic ethers, can be easily prepared by treating sodium phenoxide with a suitable alkyl halide. If I'll talk about the mechanism of this reaction, then it involves the nucleophilic attack of alkoxide ion on alkyl halide according to SN2 mechanism. A transition state is initially formed which immediately cleaves to give the desired product. There are also limitations of the Williamson synthesis. Students, in the preparation of unsymmetrical ethers, a proper choice of the reactants is necessary. If we want to prepare unsymmetrical ethers, the halide used should preferably be primary, because Williamson synthesis occurs by SN2 mechanism and primary alkyl halides are most reactive in SN2 reactions. So my dear students, best yields of unsymmetrical ethers can be obtained when alkyl halides are primary. However, the alkoxides may be primary, secondary or tertiary. The secondary and tertiary alkyl halides, if used, may form alkenes as major product due to elimination process. If tertiary alkyl halide is used, an alkene is the only product and no ether is formed. For example, if we want to prepare tertiary butyl ethyl ether, then we should take ethyl bromide and sodium tertiary butoxide. However, if we use tertiary butyl bromide and sodium ethoxide as reactants, then the major product would be 2-methylpropene and ethanol. This is because alkoxides are not only nucleophiles but strong bases as well. They react with alkyl halides, leading to elimination reaction. A very important thing here is that due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution, giving a mixture of both elimination and substitution products. Now let's start with the physical properties of ethers. First, we will discuss about physical state of ethers. Lower members like dimethyl ether, methyl ethyl ether are gases, and higher members are low boiling point liquids with a pleasant smell. Next, we will discuss about dipole moments. Ethers have bent or angular structure like water. Due to greater electronegativity of oxygen than carbon, the carbon-oxygen bonds are slightly polar and therefore the ethers have resultant dipole moment. My dear students, since the two carbon-oxygen bonds are inclined to each other at an angle of about 110 degree, the two dipoles do not cancel each other. As a result, ethers have resultant dipole moment. Next, we will discuss about boiling points. So students, ethers have low polarity and as a result do not show any association by intermolecular hydrogen bonding. Therefore, ethers have low boiling points and lower than that of isomeric alcohols and almost same as those of alkanes of comparable molecular masses. Students, there is a large difference in the boiling points of alcohols and ethers. And the reason for the large difference in boiling points of alcohols and ethers is due to the presence of hydrogen bonding in alcohols. Next, we will study about solubility. Students, solubility of ethers is comparable to those of corresponding alcohols of same molecular mass. For example, like ethanol, dimethyl ether is completely miscible with water. Similarly, both ethoxyethane and butane 1-ol are soluble in water to almost the same extent, that is 7.5 and 9.0 gram per 100 milliliter water respectively. On the other hand, pentane is almost immiscible with water. Students, solubility of ethers in water is due to the fact that like alcohols, the oxygen of ether can also form hydrogen bonds with water molecules. However, the solubility of ethers in water decreases from lower members to higher members. This may be due to increase in size of alkyl group, which decreases the tendency to form hydrogen bonding. Ethers are, however, fairly soluble in common organic solvents such as alcohols, chloroform, acetone, benzene, etc. If I'll talk about density, then all ethers are lighter than water. Now students, we will study chemical properties of ethers. Ethers are quite inert and stable compounds. They are the least reactive of the functional groups. Ethers do not combine with acids, bases, oxidizing or reducing agents under normal conditions. My dear students, the low reactivity or inert character is due to the reason that the divalent oxygen is linked to carbon atoms on both sides and has no active site, just as in case of alcohols, phenols, aldehydes and ketones. However, under drastic conditions, they do react mainly because of lone electron pair on the oxygen atom or of cleavage of carbon-oxygen bonds. Now we will study the reactions involving the cleavage of carbon-oxygen bond. First of all, we will do the reaction with halogen acids. Students, ethers are cleaved by concentrated hydroiodic acid or hydrobromic acid at 373 Kelvin and the reaction is completed in two stages. In first stage, if halogen acid is in limited amount, a mixture of alcohol and alkyl halide is formed. And in second stage, my dear students, if excess of halogen acid is available, then alcohol further reacts with halogen acid at high temperature to form alkyl halide with water. This is the net reaction. The order of reactivity of halogen acid is Hi is greater than HBr is greater than HCl. Actually students, this is based on bond dissociation enthalpy. HCl is found to be very little reactive while both Hi and HBr react in concentrated solution and also at high temperature. Now if I'll talk about the mechanism of this reaction, then in first step the ether molecule is initially protonated by halogen acid, that is Hi, hydrogen iodide, which cleaves to release H positive. Students, in second step the protonated ether is then attacked by the halide ion I negative, which acts as the nucleophile and reaction proceeds by SN2 mechanism. And students, when hydrogen iodide is in excess and reaction is carried out at an elevated temperature means at high temperature, then this reaction will be followed. Students, if I'll talk about site of cleavage, then this important thing you should need to keep in your mind that in unsymmetrical ethers, the halogen atom gets always linked to the smaller alkyl group. As we have seen, the oxygen atom of anisole will be protonated to form protonated anisole. Now, the oxygen atom is attached to the phenyl as well as methyl groups on either sides. The ring carbon involved in the linkage is sp2 hybridized with partial double bond character. At the same time, the carbon atom of CH3 group is sp3 hybridized. This means that OCH3 bond can cleave more easily as compared to OC6H5 bond when the nucleophile I negative ion is to attack. Therefore, the preferred product is CH3I and C6H5OH. Moreover, the I negative ion will prefer to attack from the side which is less sterically hindered. The obvious choice is methyl group and not the phenyl group. The phenol formed in the reaction does not react with HI because sp2 hybridized carbon atom of phenol cannot undergo nucleophilic substitution reaction resulting in idobenzene. Now if we will study the reaction with sulfuric acid, then ethers are hydrolyzed to alcohols when heated with dilute sulfuric acid under pressure. In case concentrated acid is used, a mixture of alcohol and alkyl hydrogen sulfate is formed. Now we will study the reaction with phosphorus pentachloride. In this reaction, ethers are cleaved by PCl5 to form alkyl chlorides. Now we will study the reaction with acid chlorides and acid anhydrides. In this reaction, acid chlorides react in the presence of anhydrous zinc chloride or aluminium chloride to form ester and alkyl chloride. Now we will study the ring substitution in aromatic ethers. Well students, aromatic ethers give the substitution reactions of benzene ring such as halogenation, nitration, sulphonation and friedel-Crafts reaction. First we will discuss about halogenation. Halogenation of benzene ring occurs at ortho and para positions. However, the para isomer is formed in excess. Now we will discuss about nitration. The nitration of anisole carried with nitrating mixture of concentrated nitric acid and concentrated sulfuric acid upon heating gives a mixture of ortho and para nitro derivatives. Next we will discuss sulphonation. Anisole upon sulphonation gives a mixture of isomeric sulfonic acid derivatives. Now we will study the most important reaction, friedel-Crafts reaction. Anisole undergoes friedel-Crafts alkylation and acylation reaction in the presence of anhydrous aluminium halide, which is a Lewis base, and also act as a catalyst in which alkyl and acyl groups are introduced at ortho and para positions. Now students, one question for you. How will you convert phenol to anisole? In order to convert phenol to anisole, first we will treat phenol with sodium hydroxide. It will be converted into sodium phenoxide, and then we will treat sodium phenoxide with methyl bromide and anisole will be formed. Now next question is, how will you convert nitrobenzene into anisole? First of all, there will be reduction of nitrobenzene and nitrobenzene will be converted into aniline. And now we will treat aniline with nitrous acid, and after treating with nitrous acid, aniline will be converted into phenol. And how phenol will be converted into anisole, we have discussed it in the previous reaction. Students, these are some questions related to the topic. Hope I have cleared all the concepts related to the topic. Now you can do these questions very easily. Hope you have enjoyed this session very much. Thank you so much. Goodbye.